Module 1, Lecture B, Environment Setup. By the end of this lecture, you will be able to install PyTorch 2.10 with appropriate CUDA or CPU support on the target platform. Configure a Python development environment suitable for PyTorch projects, including virtual environments and key extensions. And organize a basic PyTorch project folder structure that supports experiments, logging, and version control. Install PyTorch environment, pip and CUDA basics. Before installing a deep learning library, you should understand pip and CUDA, the main tools for managing Python software. Pausing. Pip is the default Python package manager and mainly installs packages from the Python package index. CUDA, used in Anaconda and Miniconda, can manage both Python packages and non-Python dependencies, such as CUDA libraries. This difference matters when setting up frameworks like PyTorch, because you are building a full software stack that must match your system, numerical libraries, and GPU drivers so everything works together correctly. Choosing between pip and CUDA depends on your workflow and environment needs. In research labs or teams that use Anaconda, CUDA is helpful for managing complex dependencies, GPU support, and specific library versions, and for keeping environments consistent across different operating systems. Pip is lighter and widely used, making it a good fit for system Python, virtual environments, or minimal Docker images. Understanding these typical use cases helps you select the right tool for development and deployment. When choosing between pip and CUDA, the key idea is to use them to create isolated environments instead of installing everything globally. This is important in places like university labs, where different projects may need different versions of PyTorch without causing conflicts. In production, separate environments for experimentation and stable deployments help ensure that updates do not break critical applications. By relying on pip and CUDA to build clean, reproducible setups, you make installing PyTorch more predictable, easier to share with collaborators, and simpler to revisit later. CUDA Compatibility Basics. Before installing the library, you need to understand CUDA compatibility, because it determines whether your code can actually use the GPU. CUDA from NVIDIA has its own versioning, separate from your operating system and Python, and the library is compiled for specific CUDA versions. This means the library version, your NVIDIA driver, and any separately installed CUDA toolkit must be aligned. If they are not, the package may install but will fail when you try to run GPU code, and in some cases, you may need to use an older CUDA version to match older drivers. It is important to distinguish between the CUDA runtime that comes bundled with a library and the system-wide CUDA toolkit. Many libraries include their own CUDA runtime, so you may not need the full toolkit to use the GPU. However, your NVIDIA driver must still support the CUDA version that the library uses. NVIDIA provides a compatibility matrix that shows which driver versions work with which CUDA versions. On systems where you cannot change the driver, you should check the installed driver version, see the highest CUDA version it supports, and then choose a library build that matches to avoid GPU runtime errors. When choosing between a GPU-enabled build and a CPU-only build, match your choice to your hardware and project needs. If you do not have an NVIDIA GPU or are using a CPU-only cloud service, use the CPU build to avoid unnecessary CUDA downloads. If you have a compatible NVIDIA GPU, even an older one, a CUDA-enabled build can greatly speed up neural network training and make the system more responsive. In practice, you might use CPU builds for quick local debugging and CUDA builds on GPU machines for heavy training. Understanding this compatibility helps you pick the build that best fits your hardware and performance goals. Verifying installation script. After installing your environment, you should quickly verify that everything works correctly. Check that the library can be imported, that simple tensor operations run without errors, and that the GPU is recognized if you plan to use one. This brief health check helps you catch configuration problems early. By doing it right after installation, you avoid wasting time later on models or scripts that fail due to preventable setup issues. Treat verification like preparing a shared lab workstation or production server. You need a simple, reliable check that everything works before others depend on it. When you set up a new machine, open a Python session, import your deep learning library, and try basic actions such as creating and moving tensors and checking version information. If any of these steps fail, it likely indicates missing dependencies or a mismatch with CUDA. Making this quick test a routine step ensures your environment is ready for serious experiments and model deployment. When using GPU acceleration, it is important to verify your setup because problems can be subtle and may only appear during long training runs. A good verification script should confirm that the library is installed correctly, that GPUs are detected, that tensors can be placed on them, and that simple computations run without errors. In a teaching lab, you can run this script at the start of each semester to check student machines, and in the cloud you can include it in your provisioning process to test new instances automatically. Regularly using and updating this script saves debugging time and helps ensure your experiments actually use the GPU and rest on a reliable setup. Python code. Verifying installation script. This script is used to confirm that a basic PyTorch style environment is set up correctly. It checks whether the necessary deep learning libraries can be imported and performs a few simple tensor operations. Run it after you install your deep learning tools locally to make sure everything is working as expected. This line is a comment that suggests installing the PyTorch library together with Torch Vision and Torch Audio using the pip package manager. It points to a specific download source that provides versions optimized for CUDA version 12.1, which supports GPU acceleration. Running this command in your environment manager sets up the core deep learning libraries needed for GPU-compatible work. We start by importing 3 Python modules to prepare our environment. The system module lets us access details about the Python interpreter and the system it is running on. The platform module provides information about the operating system and hardware. The random module allows us to generate random numbers so we can later set fixed seeds. Together, these imports help us check system compatibility and ensure reproducible behavior in the script. The script begins by importing the numerical library NumPy, which is designed for efficient number crunching and array handling. Using this library lets the code perform fast numeric comparisons and manipulations. This capability is important because it is later used to check whether tensor operations in the script are working correctly. We use a try-except block to import the Torch library so that any import errors are handled safely. If the import works, we mark a flag to indicate that Torch is available. If an error occurs, we catch it, set the flag to show that Torch is not available, and assign Torch to none. This way, the rest of the script can reliably check whether Torch can be used or not. The print status function is used to display information in a clear, structured format. It takes a label and a value, then prints the label followed by the value. The label is aligned to the left within a fixed width of 28 characters. This consistent alignment makes all status messages neat, readable, and easy to understand. The code first sets a fixed seed for the random module using the number 42, so that any random operations it performs give the same results every time the script runs. It then does the same for the NumPy random module, again using 42. Using these deterministic seeds makes the random number generation consistent across runs, which is important for reproducibility, debugging, and verifying results. This script first prints the Python version by reading it from the system module and trimming it to show only the version number, which helps confirm the Python environment in use. It then prints information about the platform using the platform module, giving details about the operating system and hardware. Together, these outputs provide a quick overview of the system context where the script is running. This script first checks whether the Torch library has been imported successfully. It uses a helper function to report the result, clearly stating if Torch is available or not. This check is important because it determines whether the rest of the script can safely run any operations that depend on Torch. The script first checks whether the PyTorch library has been successfully imported. If PyTorch is not available, it displays a message telling the user that they need to install it. After showing this message, the script stops running so that no code that depends on PyTorch is executed without the required library. We only run the next set of checks if importing the Torch library worked correctly. This conditional step makes sure that any operations that depend on Torch are executed only when the library is actually available. By doing this, we avoid running code that would fail or cause errors if the import had not succeeded. We print the detected version of the Torch library to confirm which one is installed and in use. This simple check verifies the environment setup and helps ensure that the Torch version is compatible with the rest of the system. Knowing the exact version can prevent issues that arise from mismatched or unsupported library versions. The code first checks whether CUDA support is available using a function from the Torch library, which determines if GPU acceleration can be used for computations. This check is important because it tells you if your system can offload work to the graphics processor for faster performance. The result of this check is then passed to a helper function that formats and prints a clear message indicating whether CUDA is available. This provides immediate feedback about the system's ability to use GPU resources. The code first checks whether CUDA is available and, based on that, chooses to run computations either on the graphics processor or on the central processor. It sets a device option to use the graphics processor if possible. Otherwise, it falls back to the central processor. After making this choice, it calls a status printing function to display which device will be used. This makes it clear to the user what hardware will handle the upcoming operations. This code uses PyTorch to create a small tensor containing the floating point values 1, 2, and 3 and places it on a previously chosen device. That device can be either the CPU or a CUDA-enabled GPU, depending on what is available. By putting the tensor on this device, any later computations on it will automatically use the processing power of that CPU or GPU. The code first checks that the tensor has 3 dimensions by comparing its shape to a 3-element tuple. It then checks the device property to confirm that the tensor is stored on the selected hardware, such as a CUDA device or the CPU. This ensures the tensor has the expected size and is located on the correct device, defaulting to the CPU when needed. This code multiplies a tensor by 2, which means it scales every element and doubles all its values. The purpose of this step is to confirm that basic arithmetic operations on tensors work correctly. By successfully performing this simple multiplication, it helps verify that PyTorch's tensor manipulation features are functioning properly in the current environment. The code moves the result tensor from the device back to the CPU, so it can work with tools that expect CPU data. This step is necessary because NumPy only operates on data stored in CPU memory. Once the tensor is on the CPU, it can be safely converted into a NumPy array. This allows further processing or verification using NumPy functions. The code first converts the tensor result into a NumPy array so it can use NumPy's numerical tools. It then creates another NumPy array with the expected values 2, 4, and 6, using the float32 data type to represent the correct result of the tensor operation. Finally, it uses NumPy's all-close comparison to check that the converted result matches the expected values within a small tolerance, confirming that the tensor operation is numerically correct. The code checks a tensor by verifying three things at once: its shape, the device it is stored on, and whether its values are correct. It combines these checks into a single true or false result. Then it calls a helper function that reports whether the tensor passed all checks. This gives a quick summary of the tensor's integrity and confirms that the environment is ready for further operations. If CUDA is available, the script prints basic information about the CUDA devices. This tells you what GPU resources PyTorch can use. Knowing this is important because the available GPU hardware can greatly affect the performance of deep learning tasks. This code checks how many CUDA devices PyTorch can see on the system. It uses PyTorch's built-in method to count the available CUDA devices. The result tells you how many GPUs are accessible for running computations. This information helps you understand the GPU resources that your PyTorch program can use. The code first checks how many CUDA devices are available. If there is at least one, it uses PyTorch to get the name of the first CUDA device. If no CUDA devices are found, it sets the device name to the word none. This way, the script works safely in environments both with and without CUDA support, always providing either a real device name or a clear placeholder. This code prints a brief summary of the available CUDA devices. It first calls a helper function to report how many CUDA devices PyTorch detects. Then it outputs the name of the first detected CUDA device, if one is present. Together, these steps give a quick overview of the GPU resources available in the current environment. At the end of the process, the script prints a final message to confirm that environment verification is complete. This message tells the user that all checks have been run and there is nothing more for the script to do. It clearly marks the conclusion of the verification process and signals that the script has finished executing. This script quickly checks whether PyTorch is installed and working correctly on your system. It reports the Python version and platform. Then, if PyTorch is available, confirms the PyTorch version and whether CUDA support is enabled, so it can choose the right device. It creates a small tensor, doubles it, and verifies the result to ensure basic operations behave as expected. If CUDA is present, it also reports how many GPU devices are available and the name of the first one. Overall, it provides a brief health check of your environment to confirm it is ready for deep learning tasks. PyTorch Dev Environment. Choosing Python environments. When working with deep learning libraries, it is important to manage your Python environments carefully. These environments are separate workspaces with their own Python versions and packages, which helps prevent conflicts between different projects. This isolation matters in machine learning because even small version changes in libraries like PyTorch or NumPy can change performance or behavior. By using well-managed environments, you improve reproducibility, reduce dependency problems, and make it easier to share your setup with collaborators. When managing Python environments, your choice depends on your operating system, your familiarity with tools, and your hardware. Some people use lightweight virtual environments for each project, while others prefer Conda or Mamba, especially when they need to manage both Python and non-Python packages for data science or machine learning. In shared university systems, Conda may already be installed, but on a personal laptop, simple virtual environments can be more convenient. Whatever you choose, the important thing is to stick with one method and know how to create, activate, and remove environments so each PyTorch project starts in a clean, isolated setup. When planning your Python environment for deep learning, think about how your projects will grow and where they will run, such as on a local GPU machine or in the cloud. Use an environment strategy that can be replicated across these platforms, so the same versions of PyTorch and related libraries work consistently everywhere. Teams can rely on a shared environment manager to keep everyone on the same setup and avoid version conflicts. By intentionally designing your Python environment this way, you make experimentation smoother, debugging easier, and collaboration more effective for your PyTorch projects. VS Code and Jupyter. A well-configured editor like Visual Studio Code can greatly improve productivity in modern deep learning work by letting you focus on ideas instead of tools. For PyTorch projects, it is important to choose the correct Python interpreter and set up a virtual environment inside the editor. This enables features such as auto-completion and inline documentation, which help you quickly explore new modules and remember function names. With this setup, the editor can suggest relevant PyTorch classes and methods, reducing the need to constantly check external documentation and making the learning process more efficient. Using Visual Studio Code with the Python and Jupyter extensions lets you run PyTorch notebooks directly inside the editor. This combines the interactive benefits of notebooks with the structure and version control of a full development environment. You can quickly prototype models, visualize tensors and training results, and then turn the stable parts of your notebook into reusable scripts. This way, you keep a consistent workflow as you move from experimentation to organized, production-ready code, even when preparing it for remote execution. Jupyter plays an important role in the PyTorch ecosystem because it supports exploratory, experiment-driven development. When you use it with Visual Studio Code, you can choose a specific kernel for each notebook so it runs in the correct environment with the right PyTorch version and dependencies. This is especially useful when managing multiple projects across different machines, such as a GPU server and a CPU-only laptop, because each notebook can keep its own isolated setup and avoid conflicts. As a result, tasks like logging metrics, visualizing gradients, and inspecting model weights run in the same environment as your scripts, which improves reproducibility and makes collaboration smoother. Dependency management files. When starting a deep learning project, it is important to record exactly which Python packages and versions you use. Dependency management files serve this purpose by acting as a contract that lets you recreate the same environment later. In a PyTorch workflow, this includes the main framework along with data and visualization libraries. Sharing such a file with collaborators allows everyone to set up a matching environment, which makes the project more reproducible and reliable. When managing dependencies for PyTorch projects, you can begin with a simple list of required packages without fixing exact versions, which allows some flexibility for minor updates. As the project matures, especially for publications or deployments, you should lock in specific versions to guarantee consistent and reproducible results. In team settings, using precise dependency files ensures everyone works with the same library versions, avoiding compatibility problems and letting the group focus on modeling and analysis. Dependency management files record exactly which software environment each version of your project uses, and they should be committed to version control along with your code. This creates a reliable history so you can recreate past setups, even as team members, hardware, or tools change over time. Continuous integration and other automated systems also rely on these files to build clean environments for testing and training. Treating your dependency file as seriously as your code helps keep PyTorch projects stable, reproducible, and easy to collaborate on. PyTorch project structure. Source and tests layout. When starting a PyTorch project, it is important to separate your main application code from your tests, because this structure affects how the project grows and is maintained. A common approach is to keep the core source code in one directory and place tests in a parallel tests directory. This clear layout makes it easier to navigate the codebase, verify that each component works correctly, and reduce bugs. Following this kind of structure mirrors professional software practices and helps turn your PyTorch work into a maintainable system that can evolve over time. When organizing your source directory, structure files by their responsibilities instead of putting everything into one script. Separate modules for data handling, model definitions, training, evaluation, and utilities so each part of the project has a clear role. For example, keep tokenization and dataset preparation together, model architectures in another place, and training logic in its own module. This modular design makes it easier to swap components, such as trying a new model, without rewriting the whole system. It also encourages reusable functions and classes, which helps both future work and collaboration. When organizing a PyTorch project, structure your tests to mirror your source code, so each important module has a matching test that checks its behavior. In a reinforcement learning project, for example, you might verify that environments reset correctly and that policies produce outputs with the expected shapes. Even simple tests, such as running a model's forward pass on synthetic data, can quickly reveal tensor mismatches and similar issues. This mirrored test setup acts as a safety net, and when combined with continuous integration, helps keep your codebase reliable as it changes over time. Configs and logs. For reproducible and debuggable PyTorch projects, it is important to organize your configurations and logs in a clear way. Use one directory for configuration files and another for logs or experiment outputs. This separates inputs, such as model settings and data paths, from outputs like training results and metrics. With this structure, you can easily trace which configuration produced which results, which is especially helpful when revisiting a project or working with collaborators. Store your experiment settings in a configuration directory that mirrors your project structure, such as separate files for different models or datasets. Each file should define key parameters like batch size, learning rate, and optimizer, instead of hard-coding them in your scripts. This approach makes it easier to version, reuse, and compare configurations across experiments. For example, a medical image classification project could keep distinct configuration files for MRI and ultrasound, reducing errors and simplifying parameter sweeps. When running experiments, set up a main logging folder where each run has its own subfolder named with a timestamp or other identifier. In each run's folder, save the configuration, training logs, model checkpoints, and important outputs such as plots or metrics. This structure makes it easy to compare different experiments, like changing learning rates or data augmentation, because you can quickly find all details for each run. Keeping logs separate from your source code also keeps the repository clean and makes it easier to use visualization tools and backup systems while preserving your full experimental history. Git and ignore files. When starting a PyTorch project, it is important to use version control and carefully choose what to track in your repository. You should include essential items like source code and configuration files, but avoid machine-specific or very large files such as raw datasets and model checkpoints. Setting up good ignore rules keeps the repository clean, prevents sharing unnecessary or sensitive data, and supports an efficient workflow. This way, the team can collaborate on scripts and settings while storing heavy data and model weights in more appropriate locations. In most projects, you place an ignore file at the root of your repository to tell the version control system which files and folders to skip. For a PyTorch project, this usually includes experiment outputs such as logs and model checkpoints, along with environment-specific directories. Defining these patterns keeps large numbers of temporary or generated files from each training run out of version control. This prevents your repository from becoming cluttered and helps you and your collaborators focus on meaningful code changes instead of sifting through unnecessary files. A careful ignore setup in your PyTorch project helps separate essential code and configuration from temporary experiment outputs. This makes it easier for collaborators to clone the repository, set up their environments, and run experiments without cluttering version history. It is especially important when working with sensitive data, such as medical or financial information, to avoid accidentally committing confidential files. With organized directories and a disciplined ignore strategy, your project can scale with experiments, stay lightweight, and keep a clear record of the code and settings that matter. In this lecture, you learn to install PyTorch 2.10.0 with appropriate CUDA or CPU support on the target platform. Configure a Python development environment suitable for PyTorch projects, including virtual environments and key extensions. And organize a basic PyTorch project folder structure that supports experiments, logging, and version control. In the next lecture, Lecture C, we will go over Tensors fundamentals. Thank you for your attention. See you all in the next lecture.